or 2 and 7 and 2 and 8. So these are the possible combination of these values in order to form pairs of numbers. However, we are not interested in all of them. We are not interested in all of them, but sometimes we are interested in ordered pairs. Ordered pairs. What does it mean, ordered pairs? This means that the first element is always from the first set, and the second element is from the second set. So we are not interested about 1, 1 or 1, 2, because both these numbers belong to the first set. We are interested in, let's say, 1, 7. We are interested in 1, 8, 2, 7, and 2, 8. So these ordered pairs have a specifics. As I said, the first element belongs to the first set, and the second element belongs to the second set. So this kind of ordered pairs forms a relation in mathematics. Now, if there is a kind of relation such that always one element of the first set is connected to a single element of the second set, this kind of relation is known as function. So we will study functions in the course. We will not study pairs of numbers, whatever ordered pairs or relations, but we will study functions that are special relation. In our case, we have let's say 1, 7 and 2, 8. They have a kind of relationship, a special relationship between them, because each element of the second set is 6 more than the respective element of the first set. So if we have only these two pairs, 1, 7 and 2, 8, this is a narrower concept compared to relation, because there is a formula also that we can join, or we can, let's say, explain this kind of special relation that we call function using a formula. So if the set A, the first set, usually is denoted by X, and the second set usually is denoted by Y, we can write such a formula that is Y equal to X plus 6, isn't it? So because 7 is 6 more greater than 1, so we connect 1 and 7, and we connect 2 and 8. So in this regard, in this way, we form a kind of special relation that is known as function. So a function is a special relation, and we will deal with only with functions in our course here. There are many kind of functions available. There are many kind of functions. Do you see, are you following me?
Yes, I am.
Okay, so we have many kind of functions. I forgot to say that here there is the first set usually is known as domain. So the set X or the set A is known as domain in mathematics. The initial set, let's say, the set of X values, and the set of Y values is known as range. the elements of the first set are called independent variables. The dependents are or of the second set. So the first set contains independent values because we are going to give the values from ourselves, so they are independent. Then if we apply the formula, we find the corresponding values of y based on the values of x. So we give some values to x and we find the corresponding values of y. That's why we call the elements of the domain the independent variables, and the elements of the set y, or the second set, we called it as dependent variables. So the most important thing in a function is how to draw the graph of a function, in fact, because the graph of the function contains all possible ordered pairs that a function may have. So maybe you know that the graph of function contains two axes, a horizontal axis that contains the values of the independent variable of x, and the vertical axis that contains the value of y's, or the dependent variables. If we get the function that I said before, y is equal to x plus 6, and we have the two values we obtained before. So we have the values of x and y. I said before that if I have the xy, x1, the y is 7. If x is 2, y is 8. So I can write the points here. I can write the points here. Don't worry about the easy function, because today I'm giving to you only the outline of the topics. I'm not making specific exercises with you. I'm going only to explain what I have intention to do during the course. So if we write 1 and 7 here, x is 1, y it is 3, 7. This is the first point, and the second point is 2, 8. This one. Now, these 2 points belong to the graph of the function, but if the value of x, values of y are, if the values of x and y are values taken from real numbers, they have infinity values, so we can join these 2 points, so we form a kind of graph here like this. So this is a linear graph. We have many kind of graphs. We have linear graph, we have let's say exponential graph, the graph of exponential function, quadratic function graph, that is a parabola. We have inverse function graph, that is a hyperbola, and so on. But so the graph, what does the graph shows? The graph shows all pairs of numbers that belong to the function. So we have, for example, here we have 1 and 7. This is a point of the graph. 2 and 8 is here. So the graph contains all possible pairs of numbers that are in the function. I will write it here. The graph of a function contains all possible pairs of numbers that are part of the function itself. Okay, now why is important to know how to plot the graph? Not all the graphs are such simple, because there are some graphs that have the following structure. Some graphs may be like this. Some graphs may be like the one that I'm going to do now. There is a graph like this, for example. This one, and from here it continues again another part of the graph. So the graph is divided in two parts, and here we have breaking point. So the graph may sometimes be divided into separate halves, let's say, or there is a breaking point here. And it is very important to have a continuous graph, not a graph that is interrupted here, because if we have a graph that is interrupted, we cannot find the derivative of a function that is a chapter, or let's say a topic that will be covered after doing the limit and the integration as well. So the last two, let's say, topics of the program will be differentiation, that includes the derivatives, and the integration, that includes the integrals. But if the function is not continuous, so it is very important to understand what is continuity of function. Continuity of function. Why is so important? In this function here, we have a breaking point. So here we have breaking point. The function has not any value in that position. If I write some numbers to the function, if I write, let's say, some values here, I will write the function starts from 1 and goes up to 5, then the graph, then it continues from 7, let's say, and goes up to 15. If we decide to study the function at the position 6, if we decide to study the function at the position 6, we cannot study it in that position because the function is not defined in that point, because there is no graph of the function in this part here from 5 to 7. So it is a condition to study the continuity of function. So finding where there are breaking points and avoiding them if possible while studying the graph, because before starting with differentiation and integration, we must study the limit of function. So that is another important topic, limit of function. It is another part of your program. What does the limit of function means? The limit of function means what is what is the value of y, when we get closer, to a certain value of x. So basically, in simpler words, we should find what is the value of y when substituting x in a function, in the formula of a function. And so in uninterrupted graphs, it is not problem to find the limit because we can simply substitute the value of x and find the value of y. The problem is when we have this kind of function. When we have, for example, x square, so x square for let's say x smaller or equal to 2, and x plus 1 for x greater than 2. There are some kind of functions like this that are divided in two parts that don't have the same formula. And the graph of this kind of function is composed by two parts, that one is, let's say, parabola, because the function of the quadratic function has a parabolic graph, and this part here is linear. However, the function to be continuous must include three conditions. So in a function is continuous. Are you following me?
Yes, I am.
Okay. A function is continuous if there are three conditions that are met. The first is the function it must be defined at the given point, because a function is continuous at a certain point x, let's say. If it must be defined, it is defined, I'll write it is defined at that point. So we suspect here for the point 2 in this kind of graph. I will delete this graph here because I'll draw the correct graph of the function. Oh, sorry. Okay. I wanted to delete only this graph because I want to draw the correct graph of our function. So I want to draw this function here, x squared for x smaller than 2. So we can find the correct values by making a table and giving some values to the first function. So if we have x and y, x0, let's say x squared is 0, x1, 1 square is 1. But if the x is 2, 2 at 2 square is 4. So we can write these 3 points, 0, 0, 1, 1, and 2, 4. And it is a part of parabola, the first part of the graph, this one. But then we are going to, in the next, from 2 and from 3, etc., we are going to plot another graph. We are going to deal with x plus 1. So I'm writing two values here for x plus 1, x and y. So if I write the value 2, we have 3 here instead of y. And if I have the value 3, we have the value 4 here, because 3 plus 1 is 4. That's why it is better to plot the graph of the function, of the second function. It starts from 2, and we have 2, 3. 2, 3. This is the value. Then we have 3, 4. Do you see the graph is interrupted? It does not continues at the same, let's say, line, but we have two different lines. If we extend this in other values, the second part, if I write, for example, 7, I should write 8 here. If I have 8, I should write 9, and so on. So the graph continues like this. But as you see, in the point 2, we have a breaking point. That's why this kind of function cannot be continuous. And if it is not continuous, we cannot find the derivative and the integral that are very important, that we will deal with them later, during the second half of the course. So the conditions for a function to be continuous is the function must be defined at a certain point. Now our function is defined to the point to the x equal to 2, because we have for x smaller or equal than 2, so it includes also the equal, so the value 2, the first function includes the value 2 as well. So our function is defined at our point, at the point of suspension. But there is another condition for a function to be continuous. It must have a left and a right limit in that point. What does it mean, having a left and a right limit? As I said, a limit is the value of y in a given point when we substitute the x with the value of that point. So as I said before, we are not sure whether this function is continuous in the point x equal to 2, because the function is divided into two parts at the point x equal to 2. We do not suspect, for example, for x equal to 5, because we know that x equal to 5 belongs to the second part of the function, so it is continuous. It is not interrupted in that part. Also, for x smaller than 2, for x1, for x0, and so on, we do not suspect for the continuity of function. The only point that we suspect whether the function is continuous or it has a breaking point is the point x equal to 2. So in that point, we should find the left and the right limit. The left and the right limit. So if I get the left limit here, the limit of the left means when x goes to 2 but less than 2, not exactly 2. So for x smaller than 2 but going approaching the value 2, we should substitute the values of the first part of the function, because this part only includes the values of x smaller than 2. So I should write x at power 2. We replace 2 instead of x. We write 2 at power 2. It is 4. So this is the left limit. The left limit, because we get the values here from the left, from smaller than 2, not exactly at 2. Now we should find the values of the right limit, the limit when the x goes to 2 with plus. That means values that are a little smaller than 2 and but approaching 2. So for x smaller than 2, we have the second half of the function. We have another formula. We have x plus 1. So if we replace, instead of x, if we replace 2, we have 2 plus 1, it is 3. This is the right limit. However, these two values are not equal, the left and the right limit. So this is a condition for functions to be continuous. So if the left limit is equal to the right limit, then the function is continuous. If the left limit is equal to the right limit, then the function is continuous. Now the first two conditions are fulfilled in our example, but the third condition is not fulfilled because we don't have the left limit equal to the right limit, but we have two different values. So that's why our function here is not continuous. It has a breaking point at x equal to 2. I will write it. Our function, I will write here, our function is not continuous at x equal to 2 because it has a breaking point at that position or point, let's say, at that point. Do you understand what I'm saying? So it is a very important condition that a function
So please, sorry, please come back a little bit.
Yes.
Just from the conditions, just explain them again, sorry.
Yes. Okay. So if you wish, I can start today to study only the continuity of function, nothing else. I had the intention to cover for 3 or 4 minutes every topic of your program to show to make a general overview. However, if you wish, I can focus only in the continuity of function because this is a key topic of your course of the introduction in mathematics. Look, if the function is continuous, like this part here, we can find the derivation, that means the speed of the function change, but we also can find the integration, that means the surface under the graph, the surface area under the graph. But if the function has a breaking point like this, we cannot find any area because we have a gap, and a gap means that we don't have a closed area here. We don't have what to calculate. That's why it is very important to study the continuity of function in the points in which we suspect there must be a breaking point. And usually, when the function is given in two parts like this, we suspect for the point in which there is, let's say, a bordering point between two different functions that are included in the same function. So if the function is given with this form here, we have a single function, but it is composed by two different function in itself. From 2 and below 2, we have x squared as a formula for this function, but for values greater than 2, we have a different formula for the function. We have x plus 1. So when the function is given in this way, we suspect for x equal to 2 if there is a breaking point in this part or not. If there is not a breaking point in that part, we can also find the derivative and the integral of the function. But if there is a breaking point, we cannot continue anymore. So there are three conditions to have that for function to be continuous. The first condition is the function must be defined in that point. So what does it mean, a function to be defined? I could write here, let's say x smaller than 1 and x greater than 3. So the value 2 is not included in the function. So the function is not defined at x equal to 2 if we get the values that I said before. But here in our case, the function is defined in the point x equal to 2 because this part here includes that point. X equal to 2 is included in the, let's say, in the above part of the function. So the function is defined, it is okay. It must have a left and a right limit in that point. So we suspect for the point x equal to 2, we should find the left limit. That means substituting x with values that are a little smaller than 2. But we write 2 here because we want to find the exact value of the left limit. So if I substitute 1, 0, 0 power 2, it is 0. So this part here has been substituted here. And this part here has been substituted here to find the values of y, because I want to plot the graph. So for x is smaller than 2, I have taken 3 points, let's see, 0, 1, and 2, and I have substituted the value of x in the formula, and I obtained these 3 values for y, and I have plotted this graph. The same thing I have done for x greater than 2. However, I have gotten the value 2 also, although I know that 2 is not included in this part, but there are all values that are a little greater than 2, but they are much closer to 2. So I'm interested for the value 2 as well, because I want to see if these values and these values are equal. But I have two different values. In the first part of the function, if I replace x with 2, the value of y is 4. In the second function, if I substitute x with 2, I get the value of y equal to 3, because 2 plus 1 is 3. So the second function starts from here and it goes in this way. Here we have a gap, if you see, because the left limit of the function for x equal to 2 is not equal to the right limit, because the left limit is 4, the right limit is 3. So there is a breaking point here. The function does not continue without interruptions. Therefore, we cannot find the derivative of the function in this point, and also the integral of the function in this point. That's why the continuity of function is very important. So I will do 2 or 3 other exercises with you now in order to teach you how to study the continuous functions. Let's see this function here. If I have the function y equal to y is equal to 2x plus 1, and I want to show the question asks, is the function continuous at x equal to 4, let's say, or not? What should we do in this case? Because this is the demand of the exercise. Is the function continuous at x equal to 4 or not? Now we have to get 2 values, but here the function is only 1. So when the function is only 1, when it is not divided in 2 parts, most probably the function is continuous at that point. The only, let's say, case in which the function is not continuous at that point is in case if the function is not defined in that point. If we have a fraction, if the function would be y is equal to 1 over, let's say, x minus 4, the function is not defined at this point because 4 minus 4 is 0 and we cannot divide by 0. So in the point 4, in this function we would have breaking point. However, we don't suspect to have any breaking point in that part, in this kind of function. Why? Because there are 3 conditions, as I said before, for a function to be continuous. The first condition is the function must be defined. The function must be defined. At x equal to 4. Is there any let's say problem if we replace x with 4 in our function? No. If we have this function here, it is a problem if we replace x with 4 because we cannot divide a number with 0. The denominator cannot be 0, the denominator of a fraction. Here it would be a problem, the point x equal to 4, but in this function here it is not a problem. Yes, it is defined, we say. Yes, the function is defined. The function is defined at x equal to 4. It has meaning if you substitute. Yes. Okay, I will wait if you have problems. I can write them all, but it loses time. I am trying to write the most important things. If you understand the script, it is okay. So the function must be defined at x equal to 4. Is it defined? Yes. In our case, the function is defined at x equal to 4 because if we replace x with 4, we have 2 times 4 is 8 plus 1 it is 9. It is is okay. We don't have any problem if we replace x with 4. We don't risk to get, let's say, a fraction with 0 denominator or a square root with negative part, with negative here. We don't have such a problem in this kind of function. So for us, the first condition is not a problem. The second condition for a function to be continuous was to have left and right limits at that point, to have limit. So the left and the right limit, it must have a left and a right limit at that point. Now, if we replace, if we say the limit of function when x is equal to 4 with minus, that means with values that are smaller than 4, we get 2 times 4 plus 1. It is 8 plus 1. It is 9. And if we have limits of x for x is greater than 4, we have again 2 times 4 plus 1. It is 8 plus 1. It is 9. So yes, it has a left and a right limit. And the third condition is the left and the right limit be equal. In our case, they are both 9. So we say yes, our function is continuous at x equal to 4. Do you understand what I'm saying, what I'm trying to explain? So yes, thank you. For functions that are like this, that have no limits or no restrictions in the domain, that means in the value of x, like this function here, there is no problem. They are continuous everywhere in all the graph. They don't have interruption points. Only if I take this function here, this function is not defined at x equal to 4. So this is the reason why this function is not continuous. It has a breaking point. The graph of this function may be like this. Let's say, for example, it can be here, this one and this one. So here we have a breaking point. That's why we cannot either differentiate, find the derivative of the function in that point, nor the integral. So when we will discuss about the derivatives and the integrals, we will get only continuous functions. That's why continuous functions are so important. Now I will take